The question is, could you analyze the stresses in a cylindrical shaft subjected to torsion by Mohr circle? Let's see what kind of stresses we have in the shaft when subjected to a torque T. So here's the cylindrical shaft fixed at this point, right, and subjected to a torque in the counterclockwise direction at this end. Denoting the radial direction as R, hoop direction as theta, and the axial direction as Z, if I were to take a little differential element, cubical differential element, and draw the stresses on its faces, this is what I'm going to have. The torque T produces just a shear stress that acts on these faces, just like shown in this picture. The magnitude of the shear stress is, of course, given by this torsional formula, tau equal T rho over J, where T is the torque, rho is the radius, and J is the polar moment of inertia of this circle. There are no stresses on the R plane, and on these planes, of course, on the hoop plane and the axial plane, there are no other shear stresses, and there are no normal stresses either. So what we have is actually just a two-dimensional state of stress, and therefore we could simply analyze the stresses on the z theta plane or theta z plane. So here is that plane. We'll simply call this as x plane and call this as y plane. To further analyze the state of stress, let's go ahead and sketch the Mohr circle. Here's our sign convention. Tensile normal stress is positive. Clockwise shear stress is positive. The sigma tau coordinates of the x and y planes are these, and here is a sketch of the Mohr circle. It can be seen that the radius of the circle is simply tau. It then follows that the major principal stress sigma 1 is tau, minor principal stress sigma 2 is minus tau. While there are multiple ways to find the direction of the principal stresses, what I did here is this. I took this radius that points to the y plane and rotated it clockwise through an angle of 90 degrees to get to this point. This is the plane that has the minor principal stress sigma 2, right? Then I came to this xy plane and took the y-axis and rotated it through 45 degrees, which is half of this angle, and drew a plane perpendicular to that. So that's the plane that contains this principal stress, the minor principal stress. The minor principal stress happens to be a negative quantity, and therefore it is a compressive stress. The magnitude is simply tau. And the plane perpendicular to that is the major principal plane. The major principal stress is a positive quantity, and therefore that is a tensile stress. It's also clearly seen that x, y planes are the planes containing the maximum shear stresses. So the magnitudes of the maximum shear stresses are simply tau.